Let us look at P series. Now, if you recollect, in the comparison test 1 and 2, the nature of the series U sub n is found based on the nature of another series V sub n. Here, that additional series is called the auxiliary series. I had seen examples where the auxiliary series were the series 1 by n and series 1 by n square. So in general, the series 1 by n to the power of p, which is expanded like this, is called the p series. The reason why it is important is because once you understand this theorem, you will have a series where you know whether it is convergent or divergent, so that when you're working on some other series, you can use these for comparison, which we have already done. Okay, so the theorem says the P series 1 by n to the power of P is convergent if P is greater than 1. Divergent if P is less than or equal to 1. So let's take it again case by case. Let's say P is greater than 1. That was the first case. Now, just to get a visual understanding, let's say P is equal to 2. Then our P series looks like this. Series 1 by n square is equal to 1 by 1 square plus 1 by 2 square plus 1 by 3 square, which can be simplified to 1 plus 1 by 4 plus 1 by 9 plus 1 by 16 and so on. So this is how it would look like for P equal to 2. The general term is U sub n is equal to 1 by n to the power of P. 1 by n plus 1 to the power of P is less than 1 by n to the power of P when P is greater than 1. Because on the left hand side, the denominator is bigger. So that's why this less than. So that means U sub n plus 1 is less than U sub n for all n. What does that tell you? It tells us the sequence of terms of the series U sub n is monotonically decreasing. So that is one conclusion that we have arrived at. Now let us group the terms of the series such that each block has 2 to the power of k terms, where k is in the natural set of numbers including 0, so that each block is bounded by the first term of the block. Now what does this mean? Block 0, because remember it 0 is included. So the 0th block is 1 by 1 to the power of p to the power of 0. That means 1. So this block contains only one element. What about block 1? Block 1 will have 2 to the power of 1. That is 2 terms. So we have B1 containing 1 by 2 to the power of p plus 1 by 3 to the power of p. This sum will be less than 2 times 1 by 2 to the power of p. So basically what we are doing is we are substituting the denominators of all the terms in this block by 2 to the power of p, because 2 to the power of p is less than 3 to the power of p, which means this fraction is greater than this fraction. So when we do that, we end up with 1 by 2 to the power of p plus 1 by 2 to the power of p, which means basically 2 times 1 by 2 to the power of p. So this will be less than this. And this is equal to, if we take 2 down, we get 1 by 2 to the power of p minus 1. So now, the next block, b sub 2, is equal to 2 to the power of k terms after the block, previous block. So 1 by 4 to the power of p plus 1 by 5 to the power of p plus 1 by 6 to the power of p plus 1 by 7 to the power of p. Because we are talking of the block sub 2 to the power of 2 is 4. So four terms starting from the fourth term. Again, we compare it to a sum 1 by 4 to the power of p plus 1 by 4 to the power of p plus 1 by 4 to the power of p plus 1 by 4 to the power of p. This will be less than that. And that is nothing but 4 times 1 by 4 to the power of p. And this again, if we take 4 down, we get 1 by 2 to the power of p minus 1 square. Let's take one more block. This will contain 2 to the power of 3 terms. So that means 8 terms. And this sum will be less than 8 times 1 by 8 to the power of p, which is equal to 1 by 2 to the power of p minus 1 cubed. This is just to, to make sure that we understand what this statement means. Now, if we add up all the blocks, both left-hand sides and right-hand sides correspondingly, we get series 1 by n to the power of p is less than or equal to 1 plus 1 by 2 to the power of p minus 1 plus 1 by 2 to the power of p minus 1 square and so on. And if you notice that the right-hand side is a geometric series. Common ratio r is equal to 1 by 2 to the power of p minus 1. And this we know is less than 1. 1 by 2 to the power of p minus 1 is less than 1. Since geometric series is convergent for r less than 1, by comparison test 1, series 1 by n to the power of p is also convergent if p is greater than 1. So we have proved the first case. Now let's look at the next one. Now let's look at p equal to 1. So when p is equal to 1, what does it look like? We have series 1 by n is equal to 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 and so on, where n is in natural numbers. Now again, let us group the terms of the series such that each block has 2 to the power of k terms, where k is in natural numbers and 0, so that each block is bounded by the last term of the block. So in the previous case, it was the first term of the block, which means each block starts with the term with index 2 to the power of k through to the term with index 2 to the power of k plus 1 minus 1. So what does this mean? So block k will have terms from index n equal to 2 to the power of k to the term index 2 to the power of k plus 1 minus 1, where k is starting from 0. So let's look at some blocks. We have block 0 containing only the first term 1. How? Because 2 to the power of 0 is 1 and 2 to the power of k plus 1, that is 2 to the power of 0 plus 1 is 2, minus 1 is 1. So first term to first term, so only one term. A block 1 will contain 2 to the power of 1, that is 2. 2 to the power of 1 plus 1, that is 2 square. 2 square is 4. 4 minus 1 is 3. That means second term to third term. That is 1 by 2 plus 1 by. And here in block 2, we will have 2 to the power of 2. That is 4. So fourth term, 2 to the power of 2 plus 1. That is 2 cube. That is 8. 8 minus 1, 7. So up to seventh term. N is less than or equal to 2 to the power of k plus 1, which implies if we take the reciprocals, 1 by n is greater than or equal to 1 by 2 to the power of k plus 1, which are the terms of the block. Since each block K has 2 to the power of K terms, the smallest term in the block is 1 by 2 to the power of K plus 1 minus 1. Just very quickly for block 2, let's figure out 1 by 2 to the power of 2 plus 1. That means 8 minus 1, 7. So 1 by 7 is the smallest term in the block. If we replace it with an even smaller number means we basically remove this minus 1. So we end up with 1 by 2 to the power of K plus 1, which is smaller than this. Then all the terms in the block are being compared to a number which is smaller than the smallest term in the block. So, which means the sum of the terms in a block are greater than 2 to the power of K times 1 by 2 to the power of K plus 1, which is equal to 1 by 2. Now, if we simplify this by taking 2 to the power of K down, we will end up with 1 by 2. That means that each block adds at least 1 by 2. And remember, there are infinitely many blocks. So, the series satisfies the condition that it is greater than 1 plus 1 by 2 plus 1 by 2 plus 1 by 2 and so on. And hence, the series 1 by n diverges. Okay, so that was for the case of p equal to 1. Now, the case of p between 0 and 1. So, if p, let's say for example 1 by 2, then the series would look like this. Series 1 by n to the power of 1 by 2 is nothing but series 1 by root n, which is equal to 1 by root 1 plus 1 by root 2 plus 1 by root 3 and so on. We know n to the power of p is less than or equal to n. It will be equal when p is 1. But we are in this case, so it will be less than n. That implies if we take the reciprocal of both these, then the inequality changes. 1 by n to the power of p is greater than or equal to 1 by n for all n in natural numbers when p is between 0 and 1. So every term of the series 1 by n to the power of p is greater than the corresponding term of the series 1 by n. So by comparison test 1, the series 1 by n to the power of p, where p is between 0 and 1, is also divergent. So this was very straightforward. Okay, now let's look at the last case. That is when p is less than 0. So when it is less than 0, what do we have? It will look like this. Series 1 by n to the power of minus 2, let's say if p is equal to minus 2, is equal to 1 by 1 to the power of minus 2 plus 1 by 2 to the power of minus 2 plus 1 by 3 to the power of minus 2 and so on. And if we simplify it, it would be, now you notice that each term u sub n is equal to n square, which is not tending to 0. So necessary condition is not satisfied, so the series diverges. The necessary condition is that the terms of the series should tend to 0. Okay, now that was P series. Now let's look at some interesting points. We have Dirichlet series, which is an infinite series a sub n divided by n to the power of p. Basically, this defines a family of series. We get the p series if a sub n is equal to 1, which is 1 by n to the power of p. When a sub n is equal to 1 and p is equal to 1, we call it the harmonic series. When a sub n is equal to 1 and p equal to 2, we call it the Basel series. When a sub n is equal to 1 and p is greater than 1, basically, in that case, it defines the Riemann zeta function. It is just an interesting aspects of P series. Now, just like we have P series where when P equal to 1, it is called harmonic series, we have something called as hyperharmonic series. So we start with the harmonic series. The partial sum h sub n is equal to k equal to 1 to n of 1 by k. Now, which means sequence of partial sums would be h1, h2, h3 and so on. So the series formed by the sequence of partial sums is the first hyperharmonic series. If we repeat the process with the sequence of partial sums, we get the next hyperharmonic series. That is h sub n, and on top we write 2 in brackets to avoid confusing it with squaring. And this is called the second hyperharmonic series, which means we can keep going forward. We can have third hyperharmonic series, fourth, fifth, sixth, and so on. So that was P series. Now, if you found this session helpful, please do like, share, and subscribe. Comment suggestions are always welcome. Thanks for watching. See you in the next session. That's it for now.